I'll start recording. Okay, so hello everyone. I'm MD Monarul Islam Bhuya, and I'm a PhD student at Cosmos Research Center at the University of Arkansas Little Rock. And today I'll be giving a lecture on algorithmic bias, content trap, in recommendation networks. So this is my research topic actually, and I will share the insights, what I've been doing so far, and while I'll be presenting, if you have any questions or concern, please let me know. And I've also provided my email address and website, so if you can reach out to me after the class regarding any topic related to content trap in recommendation networks, feel free to reach out to me again. Thanks. So with that, I'm gonna start. Yeah. So before diving into the full presentation, let's just give you a brief overview what I'm gonna cover today. So I will go ahead with the motivation of the research and why I find it intriguing, and you may also find it interesting as well. I'll then move on to the introduction section where I will discuss some of the definitions of what content trap is or what homophily or filter bubble means. And then I will go in the data pipeline, meaning how we collected the data and what are the necessary steps to follow before you collect all of this data. And then we will also see the case studies, which I mean, which case studies we took for our study. And then we will go over the network analysis part as well as network resiliency. Then we will go over a brief discussion about topic modeling as well as the attraction and retention mechanism. After that, we will also discuss the unweighted versus weighted topical uniformity. Then I will share you some of the results that I had and also the implications of this content trap in our society. And finally, I will conclude our lecture with question and answering. Yeah. So the motivation behind this study is that we all use social media platforms such as Facebook, Instagram, and you can name a few. So the reason is that social media is widely available, and every day we are generating huge amount of data. Also, every almost every other platforms use recommendation engine or recommendation algorithm to maximize their business value, or in terms of, if you say in terms of user's perspective, they want to try to engage you more to their social media platform so that you can spend more time on their platform and make a business for them as well. So specifically, we focus on YouTube for our content trap study. Is because YouTube algorithm drives almost 70% of the total watch time. So basically, whenever you go onto YouTube, and you will obviously see there is a bunch of videos in front of you. Those are based on your past interaction with the YouTube or whatever you prefer to watch. Based on that, you will get those kind of suggestions. So we wanted to study that if this kind of personalization can lead to entrapment or like creating filter bubbles or content trap, or whether or not. And this goes beyond echo chamber or filter bubble. I will discuss why, and as well as give you some examples and how from echo chamber to naming content trap, what are the characteristics were involved. After that, I will go over what content traps and algorithmic bias brings to online discourse as well. So these were the first few motivation for us to study this research. Next, I'll give you a brief introduction. So setting the stage, right? I mean, we already know echo chamber. I mean, some of you may know echo chambers or filter bubbles where users are repeatedly forced into, in explicitly or implicitly into similar types of contents. But what is a content trap? Is it just another name for homophily or echo chambers? It's not. So you can see the definition here says a content trap is a structurally cohesive and topically uniform region within a recommendation network that repeatedly attracts and retains users. So if you go, it means that the structurally cohesive network, meaning that in a network, this structure is kind of tightly knit among other nodes compared to other nodes. And high topical uniform region means that within this cluster, most of the since I'm working on the YouTube video, so most of the videos has kind of similar topic, and it's coming from a recommendation network that repeatedly, meaning that the structurally cohesive group tries to capture the users more, and once they capture them, they try to retain in those videos even further. Yeah, so as I mentioned, how it differs from filter bubbles. Our analytical framework involves both structural and semantic aspect of both the recommendation engine as well as the content that lies within itself. And why this matters? Because it helps shift our understanding from user bias to systemic structure bias, meaning that we are going into the network of those recommendation engine. Even though YouTube or any other social media platform, like, they're not going to give you a social network or recommendation network. So we are getting or creating a recommendation network from the provided suggested video data, which I will show you later how we collected the data and whatnot. So as I was saying, it tries to shift our understanding from user bias to systemic structure bias by highlighting the need for network aware fairness audits and transparency in recommendation design, so that they don't uh, took us into these content traps. Rather, if they modify their recommendation algorithm or tweak some of the parameters of their recommendation engine uh, with the help of this network aspect, they can make the recommendation more fairer and transparent to users all over the world. So now let's move on to data pipeline. Like I was mentioning quite a few times, like how recommendation network is, how recommendation network is, or how it is trapping users like us into a cohesive structure. But how do you build that recommendation network, right? So YouTube simply doesn't give you your network data, right? So how do you get it? So what initially we did, we tried getting some seed words or seed videos. Let's say YouTube have millions of videos, but we first find a case study. Let's say I want to work on Trump assassination attempt. Then we find some keywords related to Trump assassination attempt and feed it to YouTube. It gives us quite a few seed videos or the initial set of videos related to Trump assassination attempt. If it's not related to that Trump assassination attempt, we discard those. Sorry, we discard those set of videos and just keep the relevant ones. Once that is done, like whenever you go into YouTube, once you click a video, you always see there is a set of or bunch of videos uh, on your right hand side as watch next videos. Those are the recommended videos, and based on the matching of your preference, the recommendations are ranked. So it gives the highest ranked one as first, then the second one, third one, and so on. So what we did, we tried to collect those set of videos. Let's say I'm starting from video A, and once I'm in video A, there are I'm sorry. So there are several other videos in the watch next. So we tried to collect the top five ones due to some hardware limitations, because we didn't have that much storage in our um, lab that time. So we took the first five recommended videos. Once we collected those five recommended videos, imagine if you were, I mean, I don't know the pointer here. So starting from this point, if this is the seed video, then we try to collect five other watch next video. And after that collection of five watch next video, once that is done, we go into the first collected watch next video and do the same process again. So we perform this task for multiple times. For our study, we perform this for 5 times. And since we are taking five watch next videos for each seed video, so it becomes multiplied by 5 times. So we started with 50, then on the second stage we got 250 videos, those used as seed videos again for the another round, and we get 1250 more videos. And once that is done, we try to connect the source and the target video. If seed video is the source, we are treating the watch next video as target, and then we are trying to build a connection between the source and the target. So after that, we try to merge together all of the videos and make networks based on the case study. And we perform this crawling based on the YouTube API, and also with the YouTube DPL, I mean API, we try to collect the metadata and enrichment, meaning that the engagements and time frame and everything based on the other API. So I'm sorry. So as I mentioned, we perform this experiment on 3 case studies. Maybe most of you don't know about what is Shengo propaganda or Uyghur conflict, but I'm sure most of you will know Trump 2024 Trump assassination attempt. So I'm gonna stop for a bit now. If you guys have any questions, please let me know. That's fine. So I'll just go ahead with the rest of the slides. Yeah, so as I mentioned, recommendation network construction, how we connected the recommendation network. Give me 1 second. Yeah, so YouTube videos represented as nodes, and the recommendation crawled across multiple hops. For this, I mentioned that we go until depth 5, and that when that is done, recommended videos became seeds for the next level, or the source of our edges in the next level. And direct edges represent the seed to recommended video links. And final networks comprises of 10,000 for 10,000, 9,000, 8,000 for different set of case studies, and it also has quite a few number of ages. And you can see the networks of our study or the case study, where the first one represents the China Uyghur discourse, and the second one represents Shenghu Propaganda YouTube Recommendation Network and 2024 Trump Assassination Network as well in C. So I'll just go over methodological pipeline in short, what we did. If on your left hand side, if this represents the YouTube recommendation network, we first try to get the structural group detection. Remember, like in the first slide, I mentioned structurally cohesive groups. So you cannot just handpick those groups. So for this, we have different social network analysis approaches. Sure, you have already known some of them by now, because Dr. Agarwal, I guess, in his first lecture has provided some of the resources on that. And then we perform network resiliency assessment. What is network resiliency assessment? We will go into a different slide. And uh, in the previous slide, we mentioned that we also collected the metadata as well as the enrichment. So here metadata involves transcripts, I mean, YouTube video transcripts, as well as video titles, video descriptions, all those. But for our topical uniformity calculation, or trying to see whether those structural cohesive groups has high homogeneous content or not, we use transcript. And we perform transcript chunking because the model or the topic model that we chose is has a limitation of token, so it cannot take more than 512 tokens. So that's why we chunk the transcript and passed on to bar topic. And after that, we try to compute the weighted topical uniformity. Once we have that, then we perform the sensitivity analysis, meaning that in different thresholds, how those network structures are performing. Are they proving as potential content trap or not? Next, let's give you a recap of the network analysis that we did. So we have centrality measures. I'm sure by now you are already familiar with that. And the first one is degree centrality, is the most easiest and the most common one. So it is the relation of number of direct connection of a node, like how many nodes, neighboring nodes are connected to one single node. That is the um, degree centrality. It shows local popularity or activity of that video or that node, if you're talking in respect to social network analysis. And then the next one is betweenness centrality. It says the fraction of shortest paths that pass through a node. That means that how critical a node is to bridge or act as a broker connecting different regions. So that's betweenness centrality. Moving on to closeness centrality, it is the inverse of the average distance from one node to all others. It tries to measure how efficiently a node can reach others. And eigenvector centrality, although it's a complicated one, but it tries to capture node's importance depend on how important its neighbors are. Meaning it tries to capture the influence through its neighboring nodes or the influential neighbors. Next, we have the network analysis for the community detection. So for community detection, you have a bunch of methods, but for our study, we focused on Louvain method. This groups nodes by maximizing modularity, um, and tries to find the dense clusters with strong internal connections. and it tries to find it repeatedly. Once the threshold recurs meet, and then it gives you the communities. And then Leiden algorithm is the enhanced version of the Leuven method. It is more stable, well connected, and produce non-fragmented communities. Next one is label propagation. It fast and scalable approach for community detection. It tries to iteratively adopt nodes neighbors until they form a cluster. And the Girvan-Newman, it's a basic community detection algorithms. Whether even though I didn't include this in our research, but I mean, as degree centrality is the very basic one, Girvan-Newman is also the primary or the primer one for the community detection algorithm. So it removes edges with the highest betweenness to uncover hierarchical community layers. And last but not the least, the focus structure analysis. It's our in-house method which identifies small, dense subgraphs that collectively tries to exert strong influence in a network. Unlike centrality measures that rank individual nodes, FSA tries to detect group level features. As you can see from the uh, figure 4, you can see on one side it has the degree centrality features, as well as on your right side you can see that it has community detection algorithms or community or group level features. So it tries to um, merge together and do perform a bi-level optimization, incorporating both user and group level features, which results in more high impact and tightly knit groups, which are ideal for analyzing structural influence. So a lot of studies have been published on these focus structures, such as key sets of commenters spreading conspiracy. In a commenters where a set of commenters trying to spread conspiracy, we collected those data and perform focus structures analysis to find the key sets of individuals who are trying to spread those type of conspiracy, or trying to find the most toxic structure in a social network, or key mobilizers in a social movement, or key structures as for our study in recommendation networks. So you can see, like, I've put together two small graphs. Those are like the focus structures from a very large network. Next, let's move on to the network resiliency. What does it mean, and why do we need the network resiliency testing? So remember that we already discussed the social network analysis approaches, and we handpick some of those social network analysis approaches and perform it on our case study data or the recommendation network. I'm sorry, just give me a moment. Yep. So what we did, we basically first applied focus structure analysis, since it is our in-house methodology, and we tried to see whether focus structures can outperform the other methods or not. So keeping focus structures, focal FSA as the baseline, we perform the FSA on this YouTube recommendation network data. So obviously we got some or quite a few structures, but not all of them uh, are or were prominent. So we have to figure out a way to get the rank, which focus structure is more prominent than the other. So how can we do that? So we come up with the idea to see uh, if we remove one focus structure from the overall network, how does it affect to the overall network? Meaning that if a network has 1,000 nodes, And if a focus structure has, let's say, 20 nodes, if we remove those 20 nodes, how the network becomes? Is it become more scattered or less scattered? If it becomes more isolated or more, there are more clusters formed, then we are treating them as influential ones. So we perform this for all of the focus structures. Um, I'm sure you can see in the slide that it says one or two. So what is that? This is the number of the focus structures. So 100 and for this data, we had like 105 focal structures, but working on 105 focal structures is just like adding more results to your analysis. But to find the critical one or the insightful one, we tried the network resiliency approach. So the number three focal structures, which had 105 nodes in that structure, when we remove that, um, obviously the number of clusters or the or I mean it become fragmented and there were a lot of clusters. And for the number nine focus structures, it had 30 nodes in it, and but when we remove that, it create the overall network or turn the overall network into 44 clusters. So by doing for all of those, we rank the top five ones which has more prominence in the network structure, and we chose those for our next analysis. So um, I will give you a brief attraction and retention mechanism by figure. I'm sure it's pretty explanatory, but I will go ahead and give you a small brief discussion about it. So for the attraction mechanism, if this is the overall YouTube recommendation for our the key group, if this is a focal structure, so how fast from outside video it goes into that key structure? How many hops does it take to go into that key structure? So if this is user one, the black lines shows that one hop, then two hop. I mean, starting from this point, it takes only two hops to go into that structure. Whereas for user two, or the blue lines, if you start from here, you go into this video and then you go into that video, then this video, then another. Finally, you go into that focus structure. So it takes five hops. So this is the attraction mechanism. And what's the retention mechanism? Retention mechanism is that once you entered into that key structure, how hard it is to get out of that structure. Let's say from this video, user one tries to go out of the video. It goes into another video which is inside the focus structure. So you are basically not out of that focus structure, right? Then you go into the another video which is also inside a focus structure or key group. Then you go outside. So basically it takes two hops, but it can also happen, I mean, in one hop you can move into another neighboring node or video that is outside of that key group. Yeah, so you can ask like, so this is just a demonstration or conceptual mechanism. So how did you perform this analysis? So for this, we perform random walk mechanism, which is like given starting from a point, I'm telling my program to go over. So it's basically a simulation study. You go from one node to another, and it tries to capture how many hops it takes to get into that focal structures, or for in the retention mechanism, how hard it is to get out of that focal structures. So this is the algorithm for the attraction analysis. I can go deep into the algorithm, but I'll explain briefly so that you understand. And if you have any questions or if you have any idea to improve this mechanism, feel free to reach out to me. So basically what it does, you have a focus structure and then it tries to capture how many hops does it take to get into that focus structure from outside any node of that structure. And because it's a random walk, and we cannot just like depend on one single walk. So we perform this multiple time to make it more generalizable. Let's say you are performing this analysis for one walk, and suddenly it gives you for attraction 50, it says 30 hops. That is like starting from any node, it takes 30 round to get into that focus structures, or 30 hops to get into that focus structures. But when you perform the same thing over and over again, and then you get the mean of the attraction, so you can in fact tell that it is generalized, even though it's a simulation study. And similarly, I mean, for I can give you the results here since I just explained this to you. So for this attraction analysis, we compared this with different centrality measures as our first uh, research, because this is a work of like 1.5 years. So when we first started, we compared with different degree centrality methods, and showed that um, focus structures is always, since we are keeping focus structures as one, I mean focus structure as the base. So attraction tries to capture how fast a walker reaches the key group, and then you can see like for most of the case study, focus structures, uh, if we are taking focus structure as the base, the attraction factor, if focus structure is 1, then the other methods, they're comparatively low than the focus structures. So meaning that um, in this mechanism, whatever methods that we had, focus structures outperform in terms of attraction for most of the case. Only in Trump assassination attempt, eigenvector groups were more prominent. So you can raise a question, I guess, here that since you mentioned centrality based are for individuals or individual nodes, and focus structure is a combination of both individual and community detection algorithms, since they took both features from these two mechanisms. So how can you compare with focus structures versus the singular node ones? So what we did here, we didn't just compare focus structures with a single or most prominent between a central value or the degree central value. What we did, remember I mentioned that we work on the network resiliency. So we ranked the focus structures. Let's say we get top 5 focus structures. And in the top 5 focus structures, there were, in the first one, there was 105 nodes. So based on 105 nodes, we first get the top 105 degree central values or closeness central values and try to connect them to form a group within themselves, and then perform the comparison. Similarly for closeness, we took the first 105 closeness central values, and then we form a group and then compare with the focus structures. And similarly for the degree and eigenvector centrality. So I'll briefly go over again retention analysis, where we perform the same random walk strategy, but this time we try to find how many times it takes to get out of the key structure. And we also perform this for 100 iteration, and I'm sorry, 50 iterations, meaning that we run the random walk 50 times, as well as we set a walk length of 100. Let's say even after 100 hops, if it doesn't get out of the um, loop, we also took consideration of that as well. For the result of the retention analysis, we also factor out the retention factor. This time, it shows that for all of the cases, the topmost focus structure outperform all the other centrality-based measures. And it shows that um, even though individual nodes detection, I mean, centrality-based algorithms or community-based algorithms perform well in identifying influential set of nodes, but focus structure analysis is far better than those structures in terms of identifying the most prominent communities related to, so I mean, YouTube recommendation network. That is, in a recommendation network, if you can identify a key network structure and whether it has good content or bad content, like polarizing content or not, it tries to attract users towards those content through the YouTube recommendation algorithm or through watch next algorithms. I mean, watch next video suggestions. And once you are in those videos, it tries to capture your attention towards those videos and push you push you towards more related to those type of content. And for next part, what we did, the random walk simulation that we were performing initially, we were just doing it from any node outside of that key structure. But hop our random walk is a different breed. It tries, um, give me a second. Okay, so it tries to capture the um, awareness of the hops. So imagine if you have a key structure, if we go into this network, if this is the network structure, so all of the videos that are connected to these videos are the first hop videos or the first hop neighboring nodes of those key structure. So we take into this into our account. And once that is done, we perform the two hop hour network, meaning that if this video is connected to this one, so this video is connected to this one, we just capture this set of videos to perform our different hop analysis. Yeah, I put the same text for both of them, I guess. Yeah. So the first one is for the uniform random walk or the initial random walk that we perform. In this case, we also, as we move forward with our papers, and once the initial one got accepted, we tried to extend our work. So we tried to see that whether FSA takes less time than the others or not. So even in this case, for different hops, focal structure still outperforms the other metrics, and it shows or it means that even from different hops, it takes less time to go into those key structures and not the vice versa for focal structure analysis. So for this study, we performed two random walk variation. One is the uniform random walk and another one is the degree biased random walk. So what is, you can ask me like, what is degree biased random walk? Degree biased random walk, here the walker or the random walker prefers or the user prefers transition toward high degree neighbors. Instead of just randomly go into a neighbor, it tries to what's my most influential neighbor in different hops. So it goes towards the high degree neighbors. So it tries to model a popularity driven exploration. So as you can see, like if the videos are high engaged or highly popular or highly connected within the recommendation network, it takes even less number of hops compared to the previous one, the uniform one. So for say for first hop, it takes 11.9 iteration on average to go into that key structure. But when it's popularity driven, it only takes 4.2 hops. So you can like get an intuition of how YouTube recommendation network works and try to get you into those set of videos to maximize their, I mean, it can be revenue or it can be like giving users a more engaging perspective within the platform. So these are the results for the hop our random walk for both uniform and degree biased. And once the structural study is done, we went into the topical uniformity where we applied BART topic model into the video transcripts for the theme extraction, meaning you now have a ranked set of network structures, as well as you now know that whether they are attracting users or retaining the users or vice versa. Like then we try to find or see whether these structures or the cohesive structures has high topical uniformity or high topical homogeneity. So we chose over traditional LEA for better semantic and contextual understanding. I mentioned previously that BART topic has a limitation, so we had to chunk the transcripts, and once that is done, we aggregated chunks to identify the topic distribution of a video. And after that, we tried to find the dominant topic for a focus structure. Let's say for the first focus structure that you saw previously had 105 videos. So, and go back to that slide, it shows that number of videos in a dominant topic is 64, meaning that topic A has come 64 uh, times, or topic A has embedded in those 64 videos, and this leads to a high topical homogeneous structure. So that we perform, and then we perform a sensitivity analysis, and based on that, if a network structure had more than a theta% of videos with one dominant topic, we are framing it as a potential content trap. But that leads to some limitations. Is that was our initial study, obviously, and then we tried to refine to find more prominent content trap that has, like, a video can have multiple topics. Topic A can have a probability of, let's say, 0.2%. Topic B can have a probability of 0.7%. So if I'm treating all of the topics probability as once, similar, then it gives us a um, it gives us a result, but it's not like scientifically more accurate. So what we did, we tried based on those BART topic soft probability distribution, we tried to capture what topic has more influence in terms of weight. So we come up with a weighted topical uniformity where it captures the intra-video topic diversity, uses BART topics soft topic distribution. It provides a probability-based measure of semantic dominance with structural groups. It also segments video transcript into paragraph level chunks as we used in our previous study. Then use BART topic to assign topic probabilities to each chunk. Like this chunk has probability um, of topic A as let's say 0.2, or in a different one 0.8, and we perform this for all the videos, and then we aggregate the probability of all of the videos. Once that is done, we try to capture the highest normalized topic weight, meaning that which topic has the highest weight among those videos. If topic B has the highest weight, we took that one, and then uh, we say that this is the topical uniformity of this network structure. Um, for a cool visualization, like I put together a figure here uh, where blue dots represents video IDs and red dots represents topics. So the topic 0 has a bunch of videos. You can see like all of those videos has only 4 topics, where topic 0 has almost 80-85% of topic 0 has embedded into the 80 or 85% of videos. So you can see that like these videos are kind of highly connected and trying to spread similar type of or similar thematic content. Next, as a small study, we performed the trap intensity score, which is a metric with the arithmetic mean of both attraction and retention score. Since we saw that focus structures almost in every case study is performing well enough, so we just did a arithmetic mean of attraction and retention factors and give a metric. So let's say given if I have given a YouTube recommendation network, I will run the analysis of both attraction and retention mechanisms and then find the trap intensity score, and can tell you that for this case study, the trap intensity score is let's say 0.7 or 0.6. And this study shows that for different social network analysis approach, focus structures still outperforms, or focus structures identifies those groups who has high trap intensity score. So I'm gonna take another pause here. I've been talking so long, so if you guys have any question, concerns, or doubts, let me know. Let me also know if you find this study interesting or not. Yeah, sure. Um, Thank you for your feedback. Uh, Let me go ahead and finish the rest of the slides. Now, now next, moving on to next, we did perform a like this is my curiosity, and like I proposed to my advisor that we saw that these groups are structurally cohesive, as well as these are highly thematic, or they have high, or I mean they have similar content or high homogeneity. My question is was to my professor was that like, so in computational social science, there are lots of persuasive theories. So 4 of them was like, one of them is social judgment theory, and another one is elaboration likelihood model, which I will give you a brief introduction of those. So I asked him and like wanted to see that within those structures, if those videos have persuasive cues or persuasive features to lead us or the users into those structurally cohesive groups. So, and once he said yes, like it was, I wanted to try and test it out. So I go ahead and tried, and fortunately, we saw that those groups who are structurally cohesive, as well as they have high topical uniformity, they also show high persuasions or high persuasive cues in those. And there is another interesting fact about it, fact that I'm gonna like discuss in a minute, uh, which also includes the engagement. So groups that are structurally cohesive, I'm repeating again, I'm sorry, but groups that are structurally cohesive, these groups also has high topical uniformity as well as high persuasive cues. These structures or set of videos also has high engagement compared to other, I mean, compared to other structures or other set of videos, which connected a lot of dots for me in my research. So let me just give you a brief introduction of what the social judgment theory is. So it says uh, people interpret new messages through the lens of their existing beliefs. So when YouTube keeps recommending content that aligns with those beliefs, users feel validated. Cues for this includes like confirmation phrases, ideological framing, or reinforcing in-group language. For the elaboration likelihood model, it explains how persuasion works through either logic or emotion. Let's say you are watching a Nike commercial. So instead of let's say instead of hiring me as their poster boy, they will obviously choose someone who is a celebrity to maximize their persuasion to the user so that they can buy those products. So we tried to find whether this kind of emotional tone or authority appeals or visuals were there or not in those videos. Then we tried to find the cognitive dissonance theory, which tells us whether people avoid discomfort from conflicting ideas. Algorithms exploit this by serving contradiction exposing content, like let's say they lied to you or try to outrage a narrative which pushes users towards one consistent viewpoint. So, like I mentioned, it this for this theory, the cues involve or include contradiction framing, outrage language, or truth revealing claims. And for narrative paradigm, it reminds us that humans are story driven. What does this mean? Like traps often center on emotionally charged or coherent stories or testimonies, conspiracies, or moral journeys, which make user stay longer because the story feels both believable uh, and meaningful to them. So, so like this type of persuasive query, persuasive cues or features was present or not. Like we try to find that. And for this task, we used prompt engineering. We performed, we give uh, not the chat GPT, rather OpenAI model, GPT-4o, and then we tried different prompts and ask for it to get the persuasive cues were present in those videos or not. If it was present, it marked them as one. If it's not, then mark them as zero, just like a binary classification. So here you can see from the image that groups that has high topical uniformity also has high persuasive, I mean, high high persuasive factors. Let's say for a video, it says that all the four persuasive cues were there. And for another video in a structurally cohesive group, it says two of them were there. So we basically average it out and then try to see it. Um, so for most of them, it showed similar results. Like when persuasive topical uniformity was high, persuasive factors was high as well as the engagement. And when we go into the individual engagements, we also see the similar pattern. Um, so finish up our lecture. Um, let's wrap with the research implications of my study on the YouTube recommendation network. So it tries to bridge both structure and the semantics. So it tries to demonstrate that algorithmic entrapment is both a network phenomenon, which are dense cohesive structures, as well as the semantic phenomenon, that is topic or narrative alignment. It also go into the advancing trap detection frameworks, which introduce a unified approach combining FSA, weighted topic modeling, and random walk dynamic to pinpoint the trap course. And then algorithmic auditing, which provides measurable indicators such as topic uniformity, attraction, retention, reachability, flow robustness. These are all the reachability and flow robustness. These were performed in the network resiliency state for evaluating algorithmic bias and content diversity. And we, as right now, just I mentioned that we also worked on the persuasion-aware modeling, which extend traditional social network analysis by integrating persuasion theories to explain why traps sustain user engagement. And for our, we want policymakers to offer a framework or to show them that we can create a framework for algorithmic explainability, which will support I'm sorry, which will support more regulatory or policy discussion towards AI-driven media ecosystems. Lastly, we also want to see the cross-platform applicability. That's for our future work. And we also want to see human algorithm interaction inside reveals, which reveals how algorithm curation subtly reshapes attitude formation or information exposure dynamics online. With that, I would like to conclude my lecture today. So if you guys have any questions regarding today's lecture or upcoming projects, please let me know. I'll try my best to answer these questions. Yes, I'll share the slides right away. Thank you so much, Mason. Okay, I guess we don't have any questions, so I have to give you a reminder. Yes, so we have already submitted your grades, and there was issue with for students grading. So we're gonna grade those, and we will share it with you, I guess, this this Monday. And it's good that like almost everyone got above 90. Um, it was in the range of 95 to 97. So yeah, if that helps. Um, that's for the last, um, last assignment grading. Yes, you are good to go. You don't have to worry. Yeah, I probably graded your assignment. All right, if you guys don't have assignment war or no, it's on the assignment one. We haven't graded project proposal because the deadline is 6th, I believe, 6th of November. So once all of the um, project proposals were submitted, then we will grade. Yeah. Mason, it's probably because we haven't published it yet on Blackboard. That's why you are not seeing it. But I'm sure you will see it by next Monday. No worries, Mason. Okay, so I think um, you guys don't have any more questions. So you all have a good night and best of luck. Thank you.